It's just show where they.
Fortunately, with the recording, we don't get those jokes in there. Yeah. So that's the good news. We can go on with normal stuff now. Okay. I believe we are recording for those absent folks. So that gets us to where Aristotle was. He says, earth, wind, and fire. Well, no, matter is everything that is around you. Anything that's tangible, it's made up of matter. And we can classify that into 4 different ways: solid, liquid, and gas. The more energy you have, the further those particles get apart and they start to act more like the vapors, the gases that are all around us, things that are so finite, so small, so spread out that we don't actually see them. But trust me, our breathing is evidence that there is a gas all around us. If you continue to add energy, of course, it would turn into lightning and plasma and electricity and those kinds of things. Okay, so if we started then to get into a complex classification of all of our matter, my golly, this is what I would think you should be able to tell me about matter at the end of the year. For today, we're just going to focus on the bottom portion of this graph. We just need to start thinking about matter as made up of tiny little particles called atoms. So that's what our focus is going to be. So again, here we are. What are we made of? Well, if someone could Google that for me on their phone. Oh, that's right. You can't Google that on your phone. I'm so sorry. I'll help you out. So we are made up somewhere in that neighborhood of about 75% water. Well, water, you're not going to find that on the periodic table. So we're made up of these complex combinations of atoms. So we got to break those down even further so we can start to understand specifically what we're made of. So if we're made of 75% water, what elements, Riverbend, are we mostly being made of then? I think that with a hydrogen and an oxygen is what they say. I believe that that is correct. And if you're following down here, yeah, you're going to see oxygen, 65% hydrogen. Now, they said they were equal. They said they were made of both of these. So, King George, help me out. Why would it be 65% oxygen but only 9% hydrogen?
Tell them. Speak with your grown-up voice.
What?
There's 2 hydrogens and 1 oxygen. So that's
well,
why.
Well, shouldn't it be different then? Shouldn't there be some more hydrogens than there are oxygens? All right, North, help us out. Can you help me out? I know you just joined, Miss Diaz, but why would we have 65% oxygen, only 10% hydrogen? What's going on there? We just said it's a 2-to-1 ratio.
They got a couple ideas. We're gonna let them go. Go.
Bring them on.
Because hydrogen weighs less than oxygen?
Yes! Knocked it out of the ballpark. Great job on the first one. That is brilliance right there. So we're going to have to learn some things about the atoms so we can make sense of this data right here, that atoms weigh different things. Well, why do they weigh different things? They're all just up on the periodic table, some numbers. Those numbers are going to mean something. We've got to be able to dissect that and be able to diagnose it and be able to talk about it. Now, there's some greats who helped us along the way. You in class, you're going to learn about these guys here. Dalton, Thomson, Rutherford, Bohr, and then maybe we'll discuss a few of things with Schrodinger and his cat and stuff like that. But there's a whole process that got to this understanding that not all atoms are the same. Elements are not the same necessarily. So to get that, we have the law of conservation of matter. That means that you can neither create nor destroy matter. It's beside you, it's tangible, it's real. Yes, you can change it into something. You can break it. You can burn it. You can blow it up. You can squish it. But you can never get rid of those atoms. They've got to exist somehow, some way in a different form. So once we understand that, we can then start making some proof and measurements, and we could do it with mass. we can do an experiment where we start with a specific weight, 80 grams in this case, and we change them, we rearrange the atoms, and we're going to end up with 80 grams at the end. We're going to have different materials, different compounds, but it's all there. And this is the conservation of mass principle. So you can neither create nor destroy matter. Matter is everything around us. And when we hold true to that principle, we can't do away with the weight. The weight's going to be the same before and after. And this is a huge, I know it seems logical to us right now, but that's because we've had thousands of years to think about this. And so we're getting better. And so we can now start to ponder what those little pieces are made of. And that's where we're heading here. So this again is the bottom half of that classification of matter. We are going to ignore the materials over on the right until later in the year when we talk about solutions. And we're going to only focus on this left side where it's either going to be an element, an atom, or it's going to be a combination, which is a compound or a molecule. So let's talk about those terms right now. So let me move you down. There we go. So atoms are the smallest form of matter. Now, you can get into physics and we could actually split atoms into subatomic particles and subatomic particles until we get down to what is theorized to be strings. But for right now, we're going to settle for atoms. We're going to say that's the smallest portion. If you combine them together, you get molecules. Any combination of atoms is a molecule. That can be different, that can be the same. So everything combined together is a molecule. However, here is where people get a little confused. A compound must be different. So all molecules are compounds. Not all compounds are molecules. No, sorry, I said that wrong. Not all molecules are compounds. Yes, not all compounds are molecules. Molecules can be the same. They can be different. Compounds must be different. Must be different elements combined together. They must look different. That is a heterogeneous combination versus molecules can be hetero or homogeneous. Okay, so now we got that settled. Let's examine the atom and what makes them different elements. It's a very simple concept that atoms are made up of subatomic particles. The number of your particles makes you a different element. So if you have one proton, you are hydrogen. If you have two protons, you are helium. If you have two protons and 4 electrons, you're still helium. If you have 2 protons and 3 electrons, you're still helium. If you have 2 electrons and 2 protons, you're still helium. But as soon as you change the proton, you change the element. That is the guiding idea behind elements. The number of protons. The number of neutrons, the number of electrons does not dictate your element. Only the number of protons. So in this example, 8 protons, you are oxygen. 79 protons, you are gold. Revisiting the molecule compound scenario, we have 7 magical elements out there. They're called the diatomics, and they can be found as molecules. All of our other elements, they are going to be monatomic. We'll talk about the Brinkelhoff. We'll talk about those. I was trying to go through the acronym, but we'll discuss those diatomics later. For right now, I just want you again to be drawing a mental image or a physical image on your page. That molecule, generally, we talk about them being the same, but they can be different. It's a generic term that means a combination of atoms, but compounds must have different elements in them. All right, so as we previously discussed, we have protons, neutrons, and electrons. The protons, they carry a positive charge. Now, that's a pay grade above me and a couple of your friends in the room here. Why is it positive? Because they have a different number of quarks. We're not going to talk about quarks, but you just have to accept that protons are positive. Electrons are negative. And neutrons have a different combination of quarks, and they come out with a neutral charge. The protons and the neutrons, they have a subatomic adhesive, again, gluons, these weird little particles that are holding it together that are similar to gravity, strong nuclear forces that are holding them together that we haven't yet detected that cause the protons and neutrons to stay together as a nucleus in the center of the atom. Orbiting around those, just like the planets are around the sun, are the electrons. The reason why they don't crash in is because they are going so fast. Just like the planets, they don't crash into the sun because they have a speed that keeps them in orbit. We have the same similar idea with the electrons. They're going so fast, close to the speed of light, that they are not able to be attracted in, even though they have opposite charges. Now, the same set of same set of subatomic particles, they have other properties beyond their charges, positive, negative, neutral. They have a mass. The proton, we're just going to say it weighs 1. We're just going to round it up. It literally has a mass of like 1 times 10 to the negative. Does anyone recall out there of the teachers? 1 times 10 to the negative, is it 29 grams or something? It's very, it's a very infinitesimally small value.
Negative 29 kilograms for
There you
the electron, or for the proton, and negative 31 for the electron.
There we go. It's really, really tiny, and it's difficult to memorize. So we come up with an alternative that's pretty easy to remember. It's a whole number. We're going to say protons weigh 1, neutrons weigh 1, and electrons, because they're so small, we're just going to say insignificant. They are 2,000 times smaller. We're not going to get 2,000 electrons around a nucleus anyway, so we're just going to say they weigh 0. So we're done with that. So 1, 1, and 0 is their weights. Their charges were positive, neutral, and negative. All right, what do we do with all this information? Well, we want to represent it, and we're going to put it on a periodic table for you eventually. And what you'll notice is that top whole number, that's the atomic number, that's the number of protons. So we organize our periodic table based on the number of protons. If we look at any element on the periodic table, so if we look at 47, it is silver, Ag. That means you know it has 47 protons. You don't have to think about or look up what that information is. You will now know that the atomic number, the whole number on the chart, it is the number of protons. In most cases, it also represents the number of electrons, but not always. Now, the atomic mass is not a whole number, so something is breaking down here. How in the world do we get to that atomic mass value? That's what the last portion of this presentation is going to talk about. Why is that not a whole number? In the previous slide you showed me, their weights were whole numbers. So how do we go from whole numbers for their weights of particles to now an atomic mass that has a decimal in it? So what it is that not all atoms of the same element are equal. We have something called an isotope. Isotopes are the same element, but they have a different mass. When I was growing up, I never met a Trent until I hit college. I met my first Trent when I was in line for a freshman orientation. And worst case scenario, he was better looking, he was taller, he was more athletic, and he had the same last name. So it was Trent Garrison and Trent Gearis. I was like, what? That's horrible. And so, of course, he overshadowed me and he won all the accolades. And I blame him to this day because that's how my life ended. But it gave me the desire to be where I am today. Not all Trents are the same. And I'm sure if you look at yourself and you were ever to run into another one, you would say, well, I'm better, or wow, that's a better one than me. And the same thing happens in the atom world with isotopes. They look at one another and say, well, you don't look like me. And the reason is because they have different numbers of neutrons. They can't have different numbers of protons, but they can have different numbers of neutrons. And that changes their weight. So whenever we're thinking about this atomic mass, the amount of isotopes with different weights causes the overall average to be off from a whole number. So we have two ways that we're going to represent this information about isotopes. you're going to put the name of the element, you're going to put a dash, and you're going to put something out there called the mass number. I believe I have this on the next slide. Let me see. The mass number is the sum of protons and neutrons. I'll come back to this. I'll revisit this. But just so you know how we represent those names of isotopes, there's something called a mass number. It is protons plus neutrons. Okay, so the first way that we represent an isotope is with the element's name, a dash, and that mass number. That mass number was protons plus neutrons. We as teachers, we have to provide that number of neutrons to you. That's not something that you can pull off the periodic table. We have to give that to you. We will assume that you know how to count protons, but we'll have to give you the number of neutrons. A second way that you could represent this is with the atomic symbol, the element symbol, with the mass number being in the upper left corner and the atomic number in the lower left corner. I'll show you examples of what this looks like on the next slide. So these are how we could represent these. Notice these are isotopes. They're both chlorine, but one of them has 2 more neutrons than the other. All right, Spotsy, help me out. Can you do a little math for me? Could you tell me how many neutrons are in that first chlorine 35? If we know it has 17 protons, could you help me out there? And Stafford, you're going to do the chlorine 37, so you might as well have your answer. Whoever gets it first, throw it out there.
Well, I have to unmute first. Go ahead, Stafford's ready.
Go, Stafford.
Did you hear him?
20.
20 it is. You're absolutely right. You take that top number, you subtract the bottom number, that tells you the number of neutrons. Spotsy, what you got? That's right. It's 18. Good job, team. Here's your mass number formula again. Protons plus neutrons gives you that value. If you add those together, that's that top value, or it's the number after the dash. All right. This is where our last detail. This is where we end today. The average atomic mass. Now, you're saying, whoa, whoa, whoa. What's the isotope? Everything, I forgot everything. Remember where we were. We need to be able to calculate the average atomic mass. That's that bottom number down there that is a decimal. We now have something in our head called a mass number. We have something called the atomic number. All these things, you're going to have clear, definitive, delineated notes to help you out until you get familiar with what we're trying to accomplish. There is a formula for this. If you've ever had a teacher that did weighted grades, this is how you do a weighted grade. You will take the percentage of abundance of that isotope and you multiply it by the mass number. Then you're going to take the second isotope, its percent abundance, and you multiply it by its mass number. You add those two values together and you come up with an average atomic mass. So this is where I leave you today. I have one practice problem that I will leave up on the board. I'm going to mute my mic. And you and your teachers, they're going to help facilitate this. You're going to go through this practice problem and you're going to come up with a fabulous answer. And then you're going to be proficient enough to feel like you understand what's going on in your periodic table. So with that, I conclude my speech. I'm going to mute my mic and I wish you the best. I hope you've had a wonderful first week of chemistry, of CGS, of high school, junior year. My goodness, it's going to go by so fast. So just buckle down, do a little bit of homework, do a little bit of practice. You're going to be so successful this year. Thank you so much for your time. I will see you again very soon. Thank you guys so much. Bye-bye.
Thanks, Mr. Garrison.
Bye-bye, y'all. All right. I am going to
Thank you, Mr. Garrett.
My calculator. You don't have a calculator? Use your phone.
Oh, you can.
Get your phone.
Take your calculator out.
Are we supposed to let someone say two sentences? That thing, so? Yeah. I didn't know. How.
We like look at them.
We get blessings again now?
All right, it's a good thing, man.
Ew.
Oh, my battery ran out. Doesn't Mr. Conley have 3 batteries over there now? I'm gonna go steal them. I'm not gonna bring him back either. You put him out there. All right, I can read it for just a second. Forgive me. Mine just died. I have to use a calculator.
Don't judge. Don't judge. I know, don't judge.
Oh, wait, actually, okay. Really sad.
Director what?
My picture of turning racist.
Oh, you did, man, that's like, you're like, God, you got the right answer.
Anyone else? Yeah, that's what I got. Probably.
Actually, for other mic.
Yeah.
Ooh.
Mr. Garrison, can I use the restroom?
See. I am notorious for going way long on my broadcast, so you'll be happy that that was one of my most disciplined